Okay, so here we got a conical tank that has its vertex down and it's 20 feet across the top and 16 feet deep. Water is flowing into the tank at a rate of 12 cubic feet per minute. And we got to find the rate of change of the depth of water when the water is 10 feet deep. Okay, so this is definitely a problem that you really want to draw a sketch for and make it clear exactly what values you're trying to find. So let's draw, let's draw a cone face down as best as we can. Cone, it's 20 feet across, so let's go from here to here. Label that 20. 16 feet deep, so from here to here. The center of the base, the vertex at 16. Little right angle symbol. And let's write the equation for a cone, for the volume of a cone, which is going to be 1/3 pi r squared times h. Don't freak out if you don't have this memorized, because usually on your exams, they'll give this to you. They won't want you to miss a problem just because you don't remember like the volume of a cone or something. But still try to try always to memorize as many formulas as you can. Okay, now this is the volume of this cone, and water is flowing into the tank at a rate of 12 cubic feet per minute. So that means the change of volume with respect to time is going to be 12. Now, we can be a little more specific with our units, 12 feet cubed per minute. Now, we want to find the rate of change of the depth of water when the water is 10 feet deep. So we're essentially looking at, let's shade in what's going on. So this shaded part represents the cone or the tank being filled in with water. This is increasing as, time increases as time goes on. So the length from here to here is a variable, and we're going to call that h. That's going to be the height of how much of the cone is being filled, or is filled at a certain moment. And then r will be the radius of this, this shaded portion. So basically the radius of this cone that's being filled, or like the radius of the cone that represents how much is currently filled, because the radius of this cone will be changing. The radius of the entire tank is always going to be 10, but the radius of this cone is going to be increasing as time goes on. Same thing with the height. And so we want to find the rate of change of the depth of water. So this is going to be our depth of water. So we want to find dH dt when the depth of water, so when this height is 10. Okay, so what we have to do is relate, we have to relate our variables h and r so that we can rewrite this equation in terms of just h. Because right now, if we can't solve for it if we have two different variables that we're going to differentiate, because we're not given enough information. Again, we're not getting enough information about what's going on. So what we can do is, we'll be a little clever here. So this shaded portion, let's go over here. So we'll have this shaded rectangle. It's going to represent, a slice of this volume here, subvolume. So this will be R, and this will be H. So again, I'm taking a slice of this. Well, so I'll show you in a minute why. So this will be that, two-dimensional. Now, the reason we do this is because the big, like the overall tank is gonna have also a right triangle built into it. And it's always gonna stay constant with its, with its radius up here, which is 10, and its height of this tall triangle, 16. So this is the right triangle, or like a cross section, so to speak, of the entire tank. And this is a cross section of the amount of the tank that's filled at a certain moment. So this is basically similar to that. So we can relate R and H and 10 and 16 in however way we want, just make sure it makes sense, because this is similar. This triangle is similar to that. And we want to relate it in a way so that we can have a variable H solved for. So that we can rewrite this equation, we can replace the R squared in terms of just H. So in other words, we can have R over 10. This tells us that R over 10 is equal to H over 16. Just by, corresponding sides. This side over that side will be equal to this side over this side, by proportions. So here we solve for R. So not, sorry, R over 10 is 8 is H over 16. I don't know why I put 10 there. So R over 10 is equal to H over 16. And then we solve this for R. So we'll get R is equal to 10/16 times H. Reducing that, we get R is equal to 5/8 H. This allows us to rewrite our equation for volume in terms of just H. Because R, we can replace with 5/8 H. So then volume will then be equal to 1/3 pi times 5/8 H squared times H. Because again, R squared is just 5/8 H squared. And so this is going to be then 1/3 pi 25 squared, 25 over 64. 64, that's not 64. Over 64 H cubed. And we can rewrite it even a little more, 25. Let's take that 25. Let's put it as coefficient. 25 over 3 times 64. What would that be? 192, I believe. Yeah, so 192 pi H cubed. Now we can simply differentiate this equation with respect to time, and we'll have just two derivatives. So what we'll have is, let's go over here so we have more room. dv dt will be equal to 25 over 192 pi. Using chain rule, we'll get times 3h squared times dh dt. Now, we know what dv dt is. We were given that it's going to be 12 feet, or 12 cubic feet per minute. And we need, and we're finding dh dt when h is 10. So we just plug 10 in for h and 12 in for dv dt, and then we can solve for dh dt. So now it just becomes an algebra problem. So we're going to get 12 over 25 over 192 pi times 3 times 10 squared dh dt. Let's just make sure we don't mess up with our algebra. So we're going to have 12 equals 10, 300. 300 times 25. 2500. 192 pi times dHdt. You know, solving for dHdt, we're going to multiply this by 192 over 2500 and divide it by pi. So we get 12 times 192 over 7500 pi. The dHdt. Let's use the power of a calculator. Oh. And we'll get about 0.097784. 84797 feet per minute. All right, there you go. Hope that helps.